All right, thank you. So hello, everyone. My name is Daniel Kosakowski. I'm a second-year graduate student at UMass Dartmouth, where I work with Dr. Robert Fisher in the computational astrophysics group. It's my honor to be able to speak to you today about some of the work we've been doing on type 1a supernovae and the prospects of using titanium-44 to differentiate between progenitors. So before I begin, I'd like to acknowledge our collaborators. As you can see, this was a joint effort with people from a large number of schools, and in fact, 5 different countries. So to start off, I'd like to give a bit of motivation behind why I became interested in the production of titanium-44. So earlier this year, I worked on a specific type 1a channel known as the dynamically driven double degenerate double detonation channel, or D6 for short. So in this scenario, accretion leads to a helium detonation on the primary, which subsequently converges to initiate a second detonation in the carbon-oxygen core. So some of the main questions related to D6 that I've been interested in are, 1, under what conditions does the core detonate and successfully produce a type 1a? 2, what conditions lead to a failed second detonation? And then finally, what would be the nucleosynthetic products and observational signatures of the surface helium detonation? So it's this final question that really motivated this work. So earlier this year, we published a paper showing our results from a failed D6 simulation. So it was a simulation where we observed the initial helium detonation without the subsequent carbon-oxygen core detonation. And in the table on the left here, we see the 12 most abundant isotopes at the endpoint of our simulation. And if you focus on the rightmost column, that would be the material that makes up the ejecta. So we end up finding in the ejecta no significant amount of nickel-56 produced. However, the ejecta does produce a decent amount of intermediate mass elements. And then the key result here was the amount of titanium-44. So we find around 1.6 times 10 to the negative 4 solar masses of titanium-44. So this shows that the amount of titanium-44 produced in the explosive helium burning could be comparable to the amount produced in core collapse supernova remnants. And then the image on the right here is a slice plot through the z=0 midplane of our simulation. So on the top panel, we see the helium density, and then the bottom panel is the titanium-44 density. And so if you look as the simulation progresses, so moving from left to right, we can see that titanium is produced over time, and it occurs where the surface layer, the helium surface layer, is being burnt. So also earlier this year, Rudiger Packmore and his colleagues had a paper where they showed a successful D6 simulation done. And in their paper, after both the helium surface detonation and the carbon-oxygen core detonation, they produced around 1.5 times 10 to the negative 3 solar masses of titanium-44. And a key difference between their simulation and ours was the mass of the surface helium. They had, I think it was around 6 times 10 to the negative 2 solar masses, where we had 3 times 10 to the negative 2 solar masses. So it's likely the mass, them having a larger amount of surface helium, is what produced so much more titanium. And currently, these 2 simulations are the only 3D simulations that have been done related to D6. So there remains many open questions that need to be addressed. Now, since all but the most massive carbon-oxygen white dwarfs are expected to have a thin helium layer, we realized that the explosive helium burning that produces this titanium-44 should occur in almost all white dwarf mergers. So comparing these two results, we realized that we could have a very rough upper and lower bound on the amount of titanium-44 produced in any white dwarf merger. And since the single degenerate scenario shouldn't undergo this same type of explosive helium burning, that motivated us to see in what way we could use titanium to potentially distinguish between double degenerate mergers and the single degenerate scenario. So the first thing that we did was to calculate the gamma ray flux of 3 galactic supernova remnants. So Kepler, G1.9 plus 0.3, and Tycho. Tycho has a detection, and the other two just have upper limits. And so the gamma ray line flux is given by this equation here, where M4 is the mass of titanium-44 in units of 10 to the negative 4 solar masses. D is the distance from the sun in kiloparsecs, and then gamma denotes 1 photon. We decided to make our predictions distance independent, so we plotted the isotropic photon count rate. So 4 pi times the flux times the distance squared as a function of time. And so the green here represents the range that we get from the two merger simulations that I just mentioned. So yeah, those are the 3D merger simulations I just mentioned. If you actually include some of the recent results from Samuel Booz and Ken Shen and their work that they did on thin helium shells, then this should bring the lower bound down by like about a factor of 2. So the red represents the range for the single degenerate near Chandrasekhar mass channel. And then we use this range of titanium-44 yields taken from Wang and Emoto, where they carried out a bunch of 2D simulations for dozens of these models with varying parameters. So we find that the detection of Tycho is consistent with the merger simulations, the range that we get from the merger simulations. And then the upper bound of Kepler is consistent with both scenarios. And then the upper bound of G1.9 is consistent with the single degenerate scenario. So now, since titanium-44 has a 60-year half-life, the next thing we did was to consider how titanium-44 might be a signature for late-time light curves. So we decided to consider SN 2019 EHK, calcium-rich transient, as well as SN 2011 FE, type 1A. So if we first just take a look at 2019 EHK, for the pseudobolometric luminosity calculation, we use the nebular model that accounts for incomplete gamma ray and positron trapping as the ejecta becomes optically thin. This model is found in detail in these two papers that are cited here. So the model here is given by this equation where there's a contribution from cobalt-56 as well as titanium-44 to the luminosity. The cobalt contribution takes into account gamma ray and positron trapping. And then the titanium-44 contribution is given by the Bateman equation solution, which is shown here. So in this equation, M is the mass of the radioactive isotope. So in this case, titanium-44. Epsilon is its specific average decay energy, and lambda is its decay rate. So the Bateman equation solution can be used to find the criteria for when the energy input of a more slowly decaying radioactive isotope always dominates a more rapidly decaying species. And so if we compare the masses of titanium-44 and cobalt-57, we find that their mass ratios need to be greater than 115 for titanium to always dominate. And then if we do the same for titanium-44 and iron-55, we get that their mass ratios need to be greater than 8.19. So it turns out that the model that most closely matches the nickel-56 yield and kinetic energy of 2019 EHK satisfies both these criteria. So this suggests that 2019 EHK should directly transition from a nickel-56 dominated phase to a titanium-44 dominated phase. And this is what allows us to just consider cobalt-56 and titanium-44 in our luminosity calculation. So for cobalt-56, we use the yields found in this Jacobson-Galan et al. Paper. And then for titanium-44, we use the yields found in a recent paper by Zanacci et al. And so we use these to get bounds for 2019 EHK. And here we plot the luminosity and also compare to the results found in the Jacobson-Galan paper. So the range of values for titanium-44 start to affect the light curve in a significant way in this region here. And so we predict that 2019 EHK should be powered by titanium-44 decay around 740 to 800 days after the explosion.
Daniel, there's about a minute left.
Okay, so the next thing we did was attempt to perform the same analysis for 2011 FE, where this time we included the effects of cobalt-57 and iron-55. We found that the estimate for the radioactive decay, for when radioactive decay will be dominated by titanium-44, should be 11 to 26.6 years for double detonations, 12.3 to 21.9 years for double degenerate mergers, and then 25.5 to 40.5 years for the single degenerate near Chandrasekhar mass scenario. However, these calculations are very rough approximation since it neglects recombination effects that will likely play a role in late times. So more detailed calculations need to be done to be able to distinguish between the recombination effects and the titanium-44 effects. And since I'm running out of time, these are my conclusions. And with that, I'll open it up for questions.
Hey, thank you very much. Questions from the audience?
Hey, Daniel, this is Ken Shen. Thanks for your talk. I had to duck out really briefly, so apologies if I missed this. Could you say something about the state of the helium shell at the time of the detonation, in particular the carbon-oxygen enrichment and what you might expect physically?
For which simulation?
The ones that you did? So any of the ones where a helium shell detonated. What was the CO mass fraction in the helium shells when they detonated?
Oh, the CO mass fraction. I'm not really remembering right now.
Okay, it's sort of a leading question. My apologies. I think they're high, right? I think they're of order 2/3 or something by mass of CO, if I remember correctly.
Yeah.
And so my one possible worry is that if that mixing is due to numerical mixing during the mergers,
yeah,
maybe the CO fractions are much lower in nature, and so then you wouldn't get nearly as much titanium production.
Right. Yeah, I'm not too sure. I think that's still an open question, right? In terms of how mixing affects the nucleosynthesis in any kind of simulations that we're doing, right?
Mm-hmm. Yeah. Yeah. Thanks.
Hi, Daniel. This is Win, UC Berkeley. Really nice talk. So if 19HK does not decay with this 44 titanium decay, like I think actually we have HC observations this late. I haven't looked at them, but if it's constraining to not indicate this titanium 44 decay, does it just mean that there might be a smaller amount, or that maybe the Zanotti models are inadequate, like not correct for this explosion? It may be consistent. I'm just wondering.
I think it could be. I think it could be either one or the other. Yeah, I think it could potentially be both.
Okay, cool.
Any more questions? I guess I have one. So I'm just curious if, and maybe you showed it already. Apologies if I missed this. Have you looked at radioactive, say, vanadium-48 production from chromium in these? Because you have some amount of helium there. I'm just wondering if that's something you've looked at.
No, we have not.
Okay.
Yeah.
Okay. Well, if we have, oh, Laura, did you have something? Yeah.
Hey, Laura Chomik here. Just curious, or could you remind me what we know about diffuse 44 titanium in the galaxy? And does that diffuse titanium tell you they have potential to constrain models of 1A progenitors?
So that's actually the next project I'm just starting to work on. Yeah, I think there is potential to see in what ways different scenarios and the rates that they occur, how they affect the abundance of titanium through the galaxy.
Okay, let's thank our speaker.